Hey, you all. Did you know that empty space, the purest vacuum you can imagine, might actually have weight? Not because it's filled with air or dust or hidden matter, but because, according to our best theories of physics, even when you remove everything, every atom, every photon, every speck of detectable stuff, what's left behind still hums with energy. And if it is energy, then by Einstein's most famous insight, energy equals mass times the speed of light squared. That means it is mass. And mass in a gravitational field weighs something. So yes, nothing might weigh something. Now, before you think this is science fiction, let me reassure you, this is not speculation. This idea lives at the heart of our most rigorously tested theory of reality, quantum field theory. And it's tied to some of the deepest mysteries in modern physics: the accelerating expansion of the universe, the nature of dark energy, and why the vacuum of space doesn't collapse into a singularity of infinite energy. This is the story of vacuum energy, and how the emptiest place in existence refuses to stay empty. So settle in, breathe slowly, let your thoughts relax, because tonight we're going to learn physics while we sleep. And we begin by asking a deceptively simple question: what is empty space? For centuries, scientists and philosophers assumed that if you could create a perfect vacuum, a region with no matter, no light, no forces acting, you'd have true nothingness, a silent, static, featureless void. But in the early 20th century, that picture began to crack. First, Einstein showed that space and time aren't rigid stages. They're flexible, dynamic, woven together into a single fabric we call spacetime. And then, with the birth of quantum mechanics, we learned something even more unsettling. At the smallest scales, reality is never still. Think of a calm lake on a windless day. From far away, the surface looks perfectly flat, smooth, motionless, serene. But if you lean in close, very close, you'd see tiny ripples constantly forming and vanishing. Not because of wind or disturbance, but because of the inherent jitter of water molecules themselves. That's a decent metaphor for what's happening in empty space. Even when nothing is there, no particles, no light, the underlying quantum fields are never quiet. They jitter. They fluctuate. They buzz with transient energy. These are called quantum fluctuations, and they're not just theoretical. We've measured their effects. The most famous demonstration is the Casimir effect. Imagine two uncharged, perfectly smooth metal plates placed extremely close together in a vacuum, just a few nanometers apart. You might expect nothing to happen. But in 1948, the Dutch physicist Hendrik Casimir predicted that these plates would actually be pushed toward each other, as if pulled by an invisible force. Why? Because between the plates, only certain wavelengths of quantum fluctuations can fit, like how only certain notes resonate in an organ pipe. Outside the plates, all wavelengths are allowed. So there are more fluctuations outside than inside, and that imbalance creates a net inward pressure. In 1997, this was confirmed experimentally, with exquisite precision. The force matched prediction to better than 1%. So empty space exerts pressure. That alone suggests it's not truly empty. But to understand why, we need to talk about what modern physics says is actually fundamental, not particles, but fields. Forget for a moment the idea that the universe is made of tiny billiard balls, electrons, quarks, photons bouncing around. That picture fails at the quantum level. Instead, quantum field theory tells us the universe is filled with invisible fields, one for each type of particle. There's an electron field, a photon field also called the electromagnetic field, a quark field, a Higgs field, and so on. These fields aren't made of anything else, they're the bedrock of reality. They exist everywhere, in every point in space, at every moment in time. Now here, the key. Particles aren't separate things moving through these fields. Particles are excitations of the fields. Think of the field like a vast ocean, calm and deep. A particle, say an electron, is like a wave rising up from that ocean. Not a separate object on the water, but a disturbance in the water itself. And when the wave settles back down, The electron is gone, but the ocean remains. That ocean, the calm, undisturbed state, is what we call the vacuum. And this is crucial. Even when the ocean looks perfectly flat, it's not truly still. At the quantum level, the field can't sit at exactly zero energy, due to the Heisenberg uncertainty principle, which says you cannot simultaneously know both the exact energy of a system and the exact time over which that energy exists. The field is forced to fluctuate. For incredibly brief moments, energy can borrow from the vacuum, as long as it's paid back quickly enough. So at every point in space, the value of each quantum field is constantly jittering, wobbling around its lowest possible value. These are vacuum fluctuations. And just like the ripples on our lake, they're not just mathematical artifacts. They have real, measurable consequences. One of the most striking is the Lamb shift, discovered in 1947 by Willis Lamb. He was studying hydrogen, the simplest atom, one proton and one electron. According to early quantum mechanics, the Bohr model, then refined by Schrödinger, the electron could occupy certain energy levels, and two particular levels, called 2s1/2 and 2p1/2, should have exactly the same energy. But Lamb found a tiny difference, about 1 part in a million. Why? Because the electron isn't just orbiting a static proton. It's immersed in the fluctuating electromagnetic vacuum. Those fleeting ripples in the photon field nudge the electron, slightly altering its energy. The effect is small but detectable, and when theorists calculated it using quantum electrodynamics, the quantum field theory of electromagnetism, the prediction matched experiment perfectly. That was the first direct evidence that the vacuum isn't passive. It's alive, seething with transient activity. Now let's turn this into something more concrete: energy. If the vacuum is fluctuating, then even in its lowest state, its ground state, it must contain energy. We call this vacuum energy, or sometimes zero-point energy. Why 0 point? Because even at absolute zero temperature, when all thermal motion has stopped, this energy remains. It's the irreducible hum of the quantum universe. How do we calculate it? Well, here, where things get tricky. In principle, every possible mode of every quantum field contributes. Think of each field as a collection of infinitely many tiny oscillators, like springs attached to every point in space. In classical physics, a spring at rest has zero energy. But in quantum mechanics, even a spring at its lowest energy state still vibrates, with an energy equal to 1/2 times Planck's constant times the frequency of the oscillator. So for a single oscillator, energy equals 1/2 times Planck's constant times frequency. Now imagine space as a grid, and at each point, a set of oscillators for each field, each with its own possible frequency. To get the total vacuum energy, you sum up 1/2 times Planck's constant times frequency for every possible frequency all the way up to infinity. But here, the problem, that sum diverges. It blows up to infinity. If you integrate over all possible momenta, or equivalently, all possible wavelengths, the total vacuum energy density becomes infinite. That can't be right. An infinite energy density would curve spacetime so violently that the universe couldn't exist. So clearly, something's wrong with this naive calculation. Physicists deal with this in two ways. First, they impose a cutoff, a maximum frequency or minimum wavelength, beyond which our current theories break down. For example, we don't trust quantum field theory above the Planck scale, where quantum gravity effects become important. The Planck length is about 1.6 times 10 to the minus 35 meters. The corresponding Planck energy is about 1.2 times 10 to the 19 giga-electron volts. So if we only sum fluctuations up to that scale, we get a finite, but enormous, estimate for the vacuum energy density. Let me do the math out loud. The energy density, that's energy per unit volume from vacuum fluctuations up to the Planck scale, is roughly Planck's constant times the speed of light, divided by 2 pi, all raised to the third power, times the Planck energy to the fourth power, divided by the speed of light to the third power, times Planck's constant to the third power. Simplifying the units and plugging in numbers, this gives a vacuum energy density on the order of 10 to the 113 joules per cubic meter. That's a 1 followed by 113 zeros, an unimaginably huge number. But now, let's compare that to what we actually observe. In 1998, two independent teams studying distant supernovae made a shocking discovery. The expansion of the universe isn't slowing down, as everyone expected. Due to gravity pulling things together, it's speeding up. Something is pushing galaxies apart faster and faster. We call this mysterious agent dark energy. And the simplest explanation, vacuum energy. In Einstein's theory of general relativity, energy, any form of energy, curves spacetime. Vacuum energy has a special property. Its energy density stays constant, even as the universe expands. Unlike matter, which dilutes as volume grows, or radiation, which dilutes and redshifts, vacuum energy remains the same per cubic meter. That means its gravitational effect doesn't weaken over time. In fact, in general relativity, a constant energy density with negative pressure produces repulsive gravity and causes accelerated expansion. So if vacuum energy is dark energy, we can measure its density from the rate of cosmic acceleration. And here's the result. The observed vacuum energy density is about 10 to the minus 9 joules per cubic meter. Let that sink in. Our theoretical estimate, 10 to the 113 joules per cubic meter. The observed value, 10 to the minus 9 joules per cubic meter. That's a discrepancy of 120 orders of magnitude, one followed by 120 zeros. This is, by far, the worst prediction in the history of science. It's called the cosmological constant problem, and it remains unsolved. To visualize the scale, if the predicted vacuum energy were equivalent to the mass of the entire observable universe packed into a single sugar cube, the actual vacuum energy would be less than the mass of a single bacterium in that same cube. What does this mean? It means one of three things, or perhaps a combination. First possibility, our calculation of vacuum energy is flawed. Maybe the infinite sum isn't physically meaningful, and only changes in vacuum energy matter, not the absolute value. In quantum field theory, we often subtract infinities, a process called renormalization, and only predict differences in energy, like in the Lamb shift. But gravity, via general relativity, cares about the total energy, including the absolute baseline. So if gravity only couples to changes in vacuum energy, not its constant part, then maybe the huge number doesn't gravitate. But we have no solid theory that explains why gravity would ignore it. Second possibility, there's a symmetry, some deep principle that forces the vacuum energy to be exactly zero. Supersymmetry, a hypothetical symmetry between matter particles and force carriers, can do this. For every bosonic field fluctuation, there's a fermionic one with opposite sign, canceling the total. But supersymmetry, if it exists, must be broken, because we don't see selectron partners for electrons or photinos for photons. And once it's broken, the cancellation is imperfect, leaving a residual vacuum energy that's still far too large, about 10 to the 60 joules per cubic meter, still 57 orders of magnitude too big. Third possibility, and the most unsettling, is that our understanding of vacuum energy and gravity is fundamentally incomplete. That quantum field theory and general relativity, though spectacularly successful in their domains, cannot be simply glued together on this point. That a theory of quantum gravity, like string theory or loop quantum gravity, is needed to resolve the paradox. Some approaches suggest spacetime itself might be emergent, not fundamental, and that the concept of vacuum energy at infinitesimal scales may be meaningless. But let's not get ahead of ourselves. Even if we don't know why the vacuum energy is so small, we do know it's non-zero because the universe is accelerating. So let's return to the original question. Can empty space have weight? Well, weight is the force exerted by gravity on a mass. And mass, via Einstein, is equivalent to energy divided by the speed of light squared. So if vacuum has energy density, say, rho sub vacuum, then it has an equivalent mass density equal to rho sub vacuum divided by the speed of light squared. Then, in a gravitational field, say, near Earth, a volume V of vacuum would have an equivalent mass of rho sub vacuum times V divided by the speed of light squared. And its weight would be that mass times the acceleration due to gravity. So weight equals rho sub vacuum times V times G divided by the speed of light squared. Now plug in the numbers. Observed rho sub vacuum is 10 to the minus 9 joules per cubic meter. Speed of light squared is 9 times 10 to the 16 meters squared per second squared. So mass density is about 1.1 times 10 to the minus 26 kilograms per cubic meter. That's roughly equivalent to 6 hydrogen atoms per cubic meter, far less than the best laboratory vacuums, which still have thousands of atoms per cubic centimeter. So for a cubic meter of pure vacuum in Earth's gravity, the weight would be 1.1 times 10 to the minus 26 kilograms, times 9.8 meters per second squared, giving about 1.1 times 10 to the minus 25 newtons. How small is that? A single grain of sand weighs about 1/millionth of a newton, so you'd need about 10 to the 19 cubic meters of vacuum, a cube over 200 kilometers on each side, to weigh as much as that 1 grain of sand. So yes, empty space has weight, but it's so unimaginably tiny that no scale on Earth could ever measure it directly. Its influence only becomes dominant when you consider the entire cosmos, where even this whisper of energy, spread over billions of light years, overwhelms the pull of all the galaxies combined. But wait, there's another way vacuum energy shows up, in particle physics. Remember how particles are excitations of fields? Well, the vacuum isn't just a passive stage, it can interact with those excitations. In fact, particles spend part of their existence as fleeting clouds of virtual particles, popping in and out of the vacuum. Take the electron. In classical physics, it's a point charge with a certain mass and charge. But in quantum electrodynamics, the electron is constantly emitting and reabsorbing virtual photons. And those photons can briefly split into virtual electron-positron pairs, like a shimmering halo around the bare electron. This cloud screens the electron's charge, making the effective charge depend on how closely you look. At large distances, you see the full screen charge, what we call the fine structure constant, about 1/137. But if you probe at extremely short distances, high energies, you penetrate the cloud and see a stronger, unscreened charge. This is called vacuum polarization, and it's been confirmed in particle accelerators. The measured magnetic moment of the electron, how strongly it interacts with magnetic fields, differs slightly from the classical prediction. That difference, the anomalous magnetic moment, has been calculated in quantum electrodynamics to 10 decimal places and matches experiment to the same precision. It's the most accurate prediction in all of science. And it depends on the structure of the vacuum. So the vacuum isn't just empty space. It's a dynamic medium that shapes the properties of everything in it. Now let's talk about the Higgs field, because this is where vacuum energy takes on an even more profound role. In the 1960s, physicists faced a crisis. Their theory of the weak nuclear force, responsible for radioactive decay, required the force-carrying particles, the W and Z bosons, to be massless, like the photon. But experiments showed they were very heavy, about 80 to 90 times the mass of a proton. How could they get mass without breaking the symmetry of the theory? The solution, proposed independently by several groups, including Peter Higgs, was this. Suppose there's a new quantum field, the Higgs field, that permeates all of space. And suppose this field has a peculiar property. Its lowest energy state, its vacuum expectation value, is not zero. Most fields, like the electromagnetic field, have a minimum energy when their value is zero. But imagine a ball sitting in a wine bottle, not at the bottom center, but in the circular rim around the base. The lowest points aren't at zero displacement, they're at some non-zero radius. That's a Mexican hat potential. The Higgs field sits like that ball, not at zero, but at a constant non-zero value everywhere in space, about 246 giga-electron volts. This is spontaneous symmetry breaking. The laws of physics are symmetric, but the vacuum state is not. And just like friction emerges when a ball rolls in a tilted landscape, particle masses emerge when other fields interact with this non-zero Higgs background. For example, the electron couples to the Higgs field with a strength called the Yukawa coupling. The mass of the electron equals that coupling times the vacuum value of the Higgs field, divided by the square root of 2. Plug in the numbers. Electron mass is about 511,000 electron volts, and you get a Yukawa coupling of about 2 × 10⁻⁶. Tiny, which is why the electron is so light compared to, say, the top quark, whose Yukawa coupling is nearly 1. So here's the deep point. The mass of every fundamental particle, except the photon and gluon, comes from its interaction with the vacuum, not from some internal essence, but from the structure of empty space itself. The Higgs field contributes to the vacuum energy, and significantly, its potential energy at the minimum is negative, about -1 × 10⁸ giga-electron volts to the 4th power. Convert that to joules per cubic meter, and you get roughly -10⁴ joules per cubic meter. That's huge and negative, so it lowers the total vacuum energy. But remember, we also have contributions from all the other fields: quarks, leptons, gauge bosons, each with their own zero-point energy. And if supersymmetry were exact, the positive and negative contributions would cancel exactly. But it's not, so we're left with a net value. And yet, observationally, that net value is positive and tiny. This suggests an incredible fine-tuning. Imagine balancing a pencil perfectly on its tip, not just for a second, but for billions of years. The combined contributions from dozens of fields, each enormous, must cancel to 1 part in 10 to the 120. That's like measuring the distance to the nearest star, Proxima Centauri, about 4 light-years away, and getting it right to within the width of a human hair. Physicists hate fine-tuning. It suggests we're missing a deeper principle. Some propose the multiverse, that our universe is one of countless others, each with different vacuum energies. In most, the value is huge and life can't form. We exist in a rare one where it's small not because of law, but because of selection. It's controversial, untestable by some definitions, but it's taken seriously because the alternative is so perplexing. But let's step back. Suppose we accept that vacuum energy is real and non-zero. What is it physically? One interpretation, the most conservative, is that it's the ground state energy of all quantum fields, as described by quantum field theory in curved spacetime. In this view, the vacuum is a physical entity with energy, pressure, and gravitational effects. That's the standard model plus general relativity picture. But there's another, more radical idea, that vacuum energy isn't energy in space, but energy of space. That spacetime itself has microscopic degrees of freedom like atoms in a solid, and vacuum energy is the zero-point motion of those. In loop quantum gravity, spacetime is woven from spin networks, discrete loops of gravitational field. In string theory, spacetime may emerge from the interactions of strings and branes. In such theories, the the cosmological constant, which is just another name for vacuum energy density in Einstein's equations, might not be a fixed number but something that can evolve or be influenced by topology, extra dimensions, or quantum entanglement. Speaking of entanglement, there's a fascinating modern idea linking vacuum energy to quantum information. The vacuum state of a quantum field is highly entangled across space. If you divide space into two regions, the vacuum on one side is entangled with the vacuum on the other, and the amount of entanglement, measured by something called entanglement entropy, scales with the area of the boundary between them, not the volume. That's strange, because entropy usually scales with volume. This area law hints that the fundamental degrees of freedom of spacetime might live on surfaces, like a hologram. In fact, the holographic principle, inspired by black hole thermodynamics, suggests that all the information in a volume of space can be encoded on its boundary. And in certain theoretical models, like anti-de Sitter space, this is mathematically precise via the AD-SCFT correspondence. Could vacuum energy be related to this holographic entropy? Some researchers think so. There's a proposal, the entanglement equilibrium hypothesis, that Einstein's equations themselves emerge from the tendency of quantum entanglement to maximize. In this view, gravity isn't fundamental, it's thermodynamic, like pressure or temperature. And vacuum energy, it might be the baseline temperature of spacetime, the irreducible noise of quantum information. This is speculative, but it shows how deeply the question of empty space's weight connects to the frontiers of physics. Let's return to something more tangible. Can we harvest vacuum energy? You've probably heard of zero-point energy devices in science fiction, machines that extract unlimited power from the vacuum. Is that possible? Almost certainly not, and here's why. Vacuum energy is the lowest possible energy state. You can't extract work from a system already at its ground state. That would violate the second law of thermodynamics. It's like trying to power a water wheel with a perfectly flat lake, no flow, no energy extraction. The Casimir effect does convert vacuum fluctuations into mechanical motion, but only by changing the boundary conditions. You have to do work to bring the plates together against other forces, and the net energy gain is zero or negative when you account for everything. No free lunch. Similarly, the dynamical Casimir effect, where moving mirrors at near light speed can convert virtual photons into real ones, requires enormous input energy to accelerate the mirrors. Again, no net gain. So vacuum energy isn't a power source, but it is a source of noise, and that matters for technology. In ultra-precise measurements, like gravitational wave detectors, vacuum fluctuations in the laser light create shot noise that limits sensitivity. Engineers use quantum squeezing, rearranging the uncertainty between position and momentum, to push noise out of the measured variable. It's like tilting the fuzziness of reality to where it hurts least. And it works. LIGO has used it to detect fainter ripples in spacetime. So even if we can't use vacuum energy, we must account for it in designing the most sensitive instruments humanity has ever built. Now let's circle back to weight, but in a different context. Suppose we have a box perfectly reflective, evacuated, rigid. Inside, pure vacuum. What happens if we add real photons, light bouncing around? The photons have energy, so by mass equals energy divided by speed of light squared, the box becomes heavier. But here's the subtlety. Even before we add photons, the vacuum inside contributes energy. If the box is small, boundary conditions suppress some vacuum modes, just like in the Casimir effect. So the vacuum energy inside the box is less than the vacuum energy outside. That means the box experiences an inward pressure, and if the walls are flexible, they'd crumple slightly. But does that change the weight? In principle, yes, because the total energy of the system includes the field energy and the stress in the walls. General relativity tells us that all forms of energy and momentum contribute to gravity, not just mass, but pressure, shear, and flux. The full source of gravity is the stress-energy tensor, a mathematical object with 16 components, encoding energy density, momentum density, pressure, and stress. For vacuum energy, the stress-energy tensor is especially simple. Energy density equals minus pressure in all directions. That's why it causes repulsive gravity in Einstein's equations. Pressure adds to the gravitational effect. For normal matter, pressure is positive but tiny, so gravity is attractive. For vacuum, pressure is large and negative, so gravity becomes repulsive. Let's write that condition clearly. For vacuum energy, pressure equals minus energy density. And in general relativity, the acceleration of the universe's expansion is proportional to energy density plus 3 times pressure. So plug in pressure equals minus energy density. You get energy density plus 3 times minus energy density, which is minus 2 times energy density. If energy density is positive, as observations show, then this is negative, meaning accelerated expansion. That's the smoking gun. Vacuum energy doesn't just have weight, it makes the cosmos stretch faster and faster. But here's a paradox. If vacuum energy is constant everywhere, how can it do work like pushing galaxies apart? Doesn't that violate energy conservation? And this is where cosmology humbles us. In an expanding universe, energy is not globally conserved. That's a direct consequence of general relativity and the lack of time translation symmetry in an evolving spacetime. As space expands, more vacuum is created, and with it, more vacuum energy. So the total energy increases. That's fine because there's no fixed background time against which to define a conserved total energy. In a static universe, energy would be conserved, but ours isn't static and hasn't been for 13.8 billion years. So vacuum energy grows as the universe grows, like a self-replicating seed. And because its density stays constant, its dominance increases over time. In the early universe, radiation ruled, then matter, and now vacuum energy. And in the far future, if it remains constant, vacuum energy will be all that matters. Galaxies beyond our local group will vanish beyond the cosmic horizon, accelerated away faster than light can cross the gap. The universe will become cold, dark, and empty, except for the hum of the vacuum itself. That's the heat-death scenario, but with a twist. Not maximum entropy from thermal equilibrium, but from exponential dilution. Now let's pause and reflect. We began by asking if empty space can have weight. We've seen that. Quantum fields never rest, they fluctuate, even in vacuum. These fluctuations give the vacuum energy, zero-point energy. That energy contributes to gravity, and observations confirm it's causing cosmic acceleration. The predicted amount is vastly larger than observed, a mystery we can't yet solve. Particle masses arise from interaction with the Higgs vacuum, so empty space gives things their substance. Vacuum energy isn't a resource to tap, but a fundamental feature shaping reality. But all of this rests on one assumption, that quantum fields are the final word. What if they're not? Some physicists, like those working on emergent gravity or analog gravity models, suggest that quantum fields themselves might be approximations. Just as sound waves in a fluid emerge from atomic motion, perhaps photons and electrons emerge from deeper, pre-geometric degrees of freedom. In such models, the vacuum isn't a sea of fields. It's a condensate like a superfluid. And fluctuations aren't fundamental, they're collective excitations. In that case, vacuum energy might be like the ground state energy of a superfluid, finite, calculable, and possibly zero. There's experimental motivation too. Certain condensed matter systems, like Bose-Einstein condensates, can simulate curved spacetime and even Hawking radiation. In these analogs, the vacuum is the condensate, and particles are phonons, sound quanta. Their vacuum energy is well-defined and small. Could our universe be such an analog? It's a long shot, but it reminds us that today's fundamentals may be tomorrow's effective descriptions. Let's take a step back in time, not just to understand what we think now, but how we got here. Because the idea that empty space could have weight didn't spring fully formed from quantum field theory. It has older, subtler roots, in a term Einstein himself introduced, then called his greatest blunder, only for it to return triumphant a century later. In 1917, just 2 years after publishing his theory of general relativity, Einstein applied it to the entire universe. At the time, everyone believed the cosmos was static, eternal, and unchanging. But his equations told a different story. Gravity should cause the universe to either expand or contract. To force a static solution, Einstein added a new term to his field equations, a constant energy density inherent to space itself. He called it the cosmological constant, denoted by the Greek letter lambda. Mathematically, it entered as an extra piece in the equation that relates spacetime curvature to matter and energy. The full equation became spacetime curvature equals 8 pi times the gravitational constant times the stress energy tensor, all divided by the speed of light to the 4th power, plus lambda times the metric tensor. Lambda represented a repulsive effect, one that grew with distance, perfectly balancing gravity on cosmic scales. For a brief moment, the universe could be static. But in 1929, Edwin Hubble discovered that distant galaxies are receding, and the farther away they are, the faster they move. The universe wasn't static, it was expanding. Einstein realized his original equations, without lambda, had predicted this all along. He abandoned the cosmological constant, reportedly calling it his greatest blunder. For decades, lambda was ignored, set to 0. Textbooks treated it as a historical curiosity. But in 1998, when supernova data revealed accelerating expansion, physicists rushed back to Einstein's old term. Lambda fit the data perfectly. The blunder was, in fact, a prophecy. And here's the irony. Einstein introduced lambda as a geometric fix, a property of spacetime itself. But quantum field theory later suggested vacuum energy would produce exactly the same effect, because in general relativity, any constant energy density behaves just like lambda. So today, when we say vacuum energy or cosmological constant, we often mean the same thing, a uniform energy inherent to space. But are they truly identical? That's a profound question. Lambda, as Einstein wrote it, is a fixed number, a fundamental constant of nature. Vacuum energy, as calculated from quantum fields, is a dynamical quantity. It could, in principle, change if the fields change. For example, if a phase transition occurs, like the Higgs field settling into its current value in the early universe. This leads to another possibility. Maybe dark energy isn't vacuum energy at all, but something that evolves. We call such models quintessence, a dynamic scalar field slowly rolling down a potential. Unlike vacuum energy, its density can change over time, and its pressure isn't exactly minus energy density, but something slightly different described by a parameter called W, where W equals pressure divided by energy density. For pure vacuum energy, W equals -1. For quintessence, W is greater than -1, maybe -0.98 or so. Current observations from the Planck satellite, baryon acoustic oscillations, and supernovae constrain W to be -1.03 plus or -0.03. So it's consistent with vacuum energy, but doesn't rule out slight dynamics. Future telescopes, like the Vera Rubin Observatory and the Nancy Grace Roman Space Telescope, will measure W with far greater precision. If they find W is not exactly -1, even by a tiny amount, it would revolutionize physics. It would mean vacuum energy isn't the full story, and that some new field is at work, subtly reshaping the fate of the cosmos. But let's return to the quantum side, because even if lambda and vacuum energy are the same, we still face the staggering mismatch between prediction and observation. And that mismatch isn't just a number, it's a challenge to our entire framework. Consider this. In quantum field theory, we calculate vacuum energy by summing over all possible field modes. But that calculation assumes spacetime is smooth and continuous, a stage on which fields play. Yet we know from black hole physics that spacetime has a finite information capacity. Jacob Bekenstein and Stephen Hawking showed that the entropy of a black hole, a measure of its hidden information, is proportional to its surface area, not its volume. Specifically, entropy equals the speed of light cubed times the area, divided by 4 times the gravitational constant times Planck's constant. That's the Bekenstein-Hawking formula. It implies a maximum of about 1.4 times 10 to the 69 bits of information in the entire observable universe. But if spacetime were continuous down to the Planck scale, the number of field modes, and thus the number of degrees of freedom, would be vastly larger. A cubic meter would contain about 10 to the 61 Planck volumes, each potentially holding multiple bits. That's 10 to the 61 degrees of freedom per cubic meter, which, over the observable universe, gives something like 10 to the 180, far exceeding the holographic bound. This suggests that our assumption of infinitely many field modes is unphysical. At some scale, perhaps the Planck scale, spacetime becomes discrete, or fuzzy, or emergent, and the number of true degrees of freedom is limited by area, not volume. If that's true, then the naive vacuum energy calculation, summing to infinite frequency, is wrong. The correct sum should only go up to the number of physical degrees of freedom, which, if holographic, scales with area. Let's try a holographic estimate. Suppose the maximum vacuum energy in a region is set by the energy of a black hole of the same size, because a black hole is the most entropic, most energetic object you can fit in a volume without collapsing. The mass of a black hole is proportional to its radius. Specifically, mass equals the speed of light squared times radius, divided by 2 times the gravitational constant. Then energy equals mass times speed of light squared. So energy equals speed of light to the 4th times radius, divided by 2 times gravitational constant. Energy density would then be that energy divided by volume, volume being 4/3 pi times radius cubed. So energy density equals 3 times speed of light to the 4th, divided by 8 pi times gravitational constant times radius squared. But this still depends on radius, meaning it's not constant. That contradicts the observation that dark energy density is constant, same today as billions of years ago. So holographic bounds alone don't solve the problem unless the relevant scale is fixed, like the cosmic horizon. There's a proposal called the holographic dark energy model, where the vacuum energy density is proportional to the inverse square of the future event horizon, the farthest point light can ever reach. That gives a constant density and predicts W slightly greater than -1. It's testable and being probed now. But even if holography explains why the vacuum energy is small, it doesn't explain why it has the precise value we observe. Why not 0? Why not slightly negative, which would cause the universe to recollapse? The value seems improbably fine-tuned for life. This brings us to the anthropic principle not as mysticism but as a logical constraint. If the vacuum energy were much larger, say 10 to the -6 joules per cubic meter instead of 10 to the -9, then galaxies could never have formed. Why? Because accelerated expansion would have begun earlier before matter had time to clump under gravity. Structure formation would be suppressed. No stars, no planets, no us. Conversely, if vacuum energy were large and negative, the universe would have recollapsed in a big crunch long before life arose. So only in a narrow window, roughly between -10 to the -9 and +10 to the -8 joules per cubic meter, can complex structures exist. We observe a value of +10 to the -9 right at the edge of that window, suspiciously so. Does that prove the multiverse? No, but it makes it plausible. In eternal inflation, a leading theory of the early universe, quantum fluctuations cause some regions of spacetime to stop inflating and form pocket universes, each with different physical constants, including different vacuum energies. Most are sterile. A few, like ours, allow galaxies, stars, and observers. Critics say this isn't science, because we can't observe other universes. But proponents counter. If a theory makes unique statistical predictions within our universe, for example, that observers should typically find themselves in universes with vacuum energy just small enough to allow structure, and that prediction matches what we see, then it's testable in principle. And interestingly, some calculations suggest that the most probable value for observers isn't 0, but something around 10 to the -120, no, 10 to the -9, precisely what we measure. The reasoning involves weighting by the number of galaxies, or the total entropy production. It's controversial but not dismissed. Still, many physicists hope for a dynamical solution, one where vacuum energy is driven to near zero by a physical mechanism, not chance. One such idea is the relaxation mechanism. Imagine a new field, the relaxation, that slowly rolls down a potential in the early universe. As it rolls, it scans the value of the Higgs mass, and thus the contribution to vacuum energy. When the Higgs mass reaches the point where atoms can form, a feedback mechanism, like the production of Higgs particles, creates bumps in the relaxation's potential, stopping its roll. The final vacuum energy is small not by tuning, but by evolution. It's elegant but requires new particles and forces beyond the standard model. So far, no evidence. Another approach comes from quantum gravity, specifically string theory. String theory allows an enormous number of possible vacuum states, perhaps 10 to the 500 each, corresponding to a different way of curling up the extra dimensions. Each vacuum has its own laws, particles, and cosmological constant. This landscape provides a concrete realization of the multiverse. But string theory also offers calculational hope. In certain controlled setups, like anti-de Sitter space, physicists can compute vacuum energy exactly using the AD-SCFT correspondence. There, a gravitational theory in bulk spacetime is equivalent to a non-gravitational quantum field theory on its boundary. Vacuum energy in the bulk maps to the ground state energy of the boundary theory, which can be calculated. In one celebrated example, the maximally supersymmetric Yang-Mills theory in 4 dimensions, the vacuum energy is exactly 0, protected by symmetry. Break the symmetry slightly, and it becomes small but non-zero. Could something similar happen in our universe? Possibly, but our universe has positive curvature on large scales, de Sitter, not anti-de Sitter, and no known exact holographic description. That's a major obstacle. We lack a full quantum theory of de Sitter space, the spacetime describing our accelerating universe. Some argue it may not even exist, that de Sitter space is only metastable, destined to decay. If true, our cosmic acceleration is temporary, and vacuum energy will eventually vanish or flip sign. There's observational hope here too. If dark energy decays, W would evolve and future surveys could detect it. Or if vacuum energy is metastable, there might be rare quantum tunneling events, bubbles of true vacuum expanding at near light speed. Inside such a bubble, the laws of physics could be different, perhaps with no atoms or no electromagnetism. We wouldn't see it coming. It would erase everything in its path. The probability is incredibly low, less than 1 in 10 to the 100 years, but not 0. Now let's turn to experiment, because however deep the theory goes, physics lives or dies by measurement. We've already mentioned the Casimir effect, direct evidence of vacuum fluctuations. But there are other tests, more subtle, more profound. One is the anomalous magnetic moment of the muon. The muon is like a heavy electron, 200 times more massive and more sensitive to virtual particles. Its magnetic moment has been measured at Fermilab to a precision of 0.2 parts per million. The standard model prediction, which includes vacuum polarization from all known particles, disagrees by about 4.2 standard deviations. That could be a sign of new particles popping in and out of the vacuum, like supersymmetric partners or dark photons. If confirmed, it would be the first direct evidence of physics beyond the standard model, and a window into the vacuum's hidden structure. Then there's the search for axions, hypothetical particles proposed to solve a different fine-tuning problem: why the strong nuclear force doesn't violate CP symmetry. Axions would be extremely light, weakly interacting, and could be produced copiously in the early universe. Crucially, they behave like a coherent field, and their lowest energy state contributes to vacuum energy. Some models tie the axions' mass to the cosmological constant, offering a link between two great puzzles. Experiments like ADMX, the Axion Dark Matter experiment, use strong magnetic fields to convert axions into detectable microwave photons. No confirmed signal yet, but sensitivity is improving. On the cosmological side, the cosmic microwave background, the afterglow of the Big Bang, encodes the universe's composition with exquisite precision. The Planck satellite measured tiny temperature fluctuations, and from their pattern, inferred that dark energy makes up 68.3% of the total energy density today, with error bars of less than 1%. But the CMB alone can't distinguish vacuum energy from quintessence. For that, we need to see how expansion has changed over time. That's where baryon acoustic oscillations come in, frozen sound waves from the early universe, visible as a preferred separation between galaxies, about 490 million light-years. By measuring that scale at different redshifts, we reconstruct the expansion history. Combined with supernova data, which give direct distance measurements, we get tight constraints on W current best fit. W equals minus 1.03, with uncertainty of plus or minus 0.03. So vacuum energy remains the simplest explanation. Yet there's a tension. Measurements of the Hubble constant, the current expansion rate, from the CMB versus from nearby supernovae and Cepheid variables disagree by about 5 sigma. The CMB gives 67.4 kilometers per second per megaparsec. The local distance ladder gives 73 kilometers per second per megaparsec. That's a 9% difference, and growing as errors shrink. Could vacuum energy be slightly inhomogeneous, stronger in some regions, weaker in others? Or could early dark energy, a field that acted like vacuum energy only in the first few 100,000 years, resolve the tension? Models exist and are being tested. Now consider gravitational waves. When two black holes merge, they ring like a bell, emitting waves at characteristic frequencies. The amplitude and frequency evolution depend on the expansion of the universe. In an accelerating cosmos, the waves are slightly stretched, a standard siren measurement. LIGO and Virgo have already used this to measure Hubble's constant, independently of other methods. With more detections, especially from space-based detectors like LISA, we'll get percent-level precision on dark energy's influence. But perhaps the most poetic test involves time itself. Atomic clocks based on the vibration of electrons in atoms are so precise they can detect time dilation from a height difference of just 1 centimeter. Now, imagine two clocks, one in a region of slightly higher vacuum energy density. Would time run differently? In general relativity, yes, because energy density curves spacetime, and curved spacetime affects the flow of time. But vacuum energy is uniform, so no local gradient, unless quantum fluctuations create temporary variations. Could a clock tick irregularly due to vacuum noise? The effect would be minuscule, but in principle, measurable with future optical lattice clocks. Some theorists propose using networks of clocks to search for correlated jitter, a signature of spacetime foam at the Planck scale. This blurs the line between quantum mechanics and gravity and brings us to the deepest question: is vacuum energy even the right concept? Let's consider an alternative view, one championed by physicists like Eric Verland, that gravity is not a fundamental force, but an emergent phenomenon like elasticity in a solid or pressure in a gas. In this entropic gravity framework, what we call gravitational attraction arises from changes in quantum entanglement entropy. The vacuum in this picture is a highly entangled quantum state. When matter is present, it disturbs the entanglement, and the system responds by pulling matter together to maximize entropy. Acceleration, like in Einstein's equivalence principle, arises from entropy gradients. In such models, dark energy isn't vacuum energy. It's the elastic response of spacetime to the de Sitter horizon. The cosmological constant appears naturally, with a value related to the horizon area. And crucially, the cosmological constant problem may dissolve because there's no sum over 0-point modes. The vacuum energy isn't gravitational, only changes in entanglement are. It's speculative and not yet able to reproduce all successes of general relativity, but it's being tested. For example, entropic gravity predicts deviations from Newton's law at very low accelerations, precisely where galaxy rotation curves seem to need dark matter. Some claim it explains those without dark matter, though most astronomers remain skeptical, citing evidence from the bullet cluster. Still, the idea that spacetime and gravity are thermodynamic, not fundamental, is gaining traction. And if true, then empty space having weight is a misstatement. It's not that space has energy. It's that the organization of quantum information manifests as energy and gravity. That's a profound shift from substance to relation. Let's bring this back to something personal to you, listening in the quiet of night. You are not separate from this vacuum. Every atom in your body, the carbon in your cells, the iron in your blood, gets its mass from the Higgs field's non-zero value in the vacuum. The stability of matter relies on the Pauli exclusion principle, a quantum rule rooted in field anticommutation, which prevents electrons from collapsing into nuclei. The light you see, even in dreams, is photons, excitations of the electromagnetic field, propagating through the same seething vacuum. When you breathe out and imagine releasing a breath into the void, that void is not passive. It pushes back with Casimir pressure. It jitters with 0-point motion. It expands with dark energy. You are immersed in a dynamic medium, ancient, invisible, essential. And here's a thought to carry into sleep. In quantum mechanics, the vacuum is not just the absence of particles, it's a state of potential. Every possible particle, every electron, every quark, every Higgs boson is latent in the fields. They don't exist until an interaction, a measurement of fluctuation, gives them temporary reality. In that sense, the vacuum is like a library of all possible stories, written in the language of quantum amplitudes. Most remain unread, but under the right conditions, in a star's core, in a particle collider, in the first moments of time, the stories are told. You too are a story the universe is telling, using the vocabulary of quantum fields, the grammar of symmetry, the punctuation of entropy, and the page on which it's written, empty space humming with weightless weight, silent with invisible sound. Now let's address a question that often arises. If vacuum energy is so small, why do we talk about it so much? Why not ignore it like we ignore the gravitational pull of a distant star? Because it's cumulative. In a lab, its effect is negligible, but over gigaparsecs across the observable universe, its repulsion overwhelms the attraction of every galaxy, every cluster, every filament of dark matter. It decides the ultimate fate of all structure. And because it's universal, it doesn't clump, it doesn't dilute. It's the same here in Andromeda, in the most distant quasar. It's the one thing besides the laws of physics themselves that connects every point in spacetime. That universality makes it a probe of the deepest symmetries. Lorentz invariance, the idea that physics is the same for all inertial observers, is woven into quantum field theory. Vacuum energy respects that. It looks the same to everyone, everywhere. If we ever detected a directional dependence in dark energy, if expansion were faster in one part of the sky, it would shatter foundational principles. So far, no such signal. The universe is isotropic to 1 part in 100,000 as seen in the cosmic microwave background. Vacuum energy is a perfect scalar, no preferred direction, no hidden structure. But what about quantum gravity effects? At the Planck scale, spacetime might foam, bubbling with virtual black holes and wormholes. Such foam could introduce tiny violations of Lorentz invariance, detectable in ultra-high-energy cosmic rays or gamma-ray bursts. If photons of different energies arrived at slightly different times from a distant flare, that could signal spacetime graininess. Experiments like the Fermi Gamma Ray Space Telescope have searched for this. So far, no evidence. Spacetime remains smoothed down to at least 10 to the minus 19 meters, far below the atomic scale. Still, the search continues. Because if vacuum energy is the bridge between quantum mechanics and gravity, then understanding it may unlock quantum gravity itself. Let's consider one final idea, one that turns the problem on its head. What if the cosmological constant isn't small, but zero, and what we're seeing as dark energy is an illusion, a misinterpretation of how gravity works on cosmic scales? That's the premise of modified gravity theories, like MOND, or its relativistic extensions, TVS and STVG. They propose that below a certain acceleration, about 1.2 times 10 to the minus 10 meters per second squared, gravity strengthens slightly, mimicking the effects of dark matter and dark energy. But while MOND works well for individual galaxies, it struggles with galaxy clusters and the cosmic microwave background. The detailed pattern of CMB fluctuations requires both dark matter and dark energy independently. Unless the modification is extremely fine-tuned, it can't reproduce all observations. Still, the possibility remains that Einstein's equations need correction not at high energies, but at low curvatures, precisely where vacuum energy dominates. This is being tested with large-scale structure surveys. If gravity is modified, the growth rate of cosmic structures, how fast clusters form, would differ from general relativity predictions. Current data from Dacey and Euclid slightly favor standard gravity, but uncertainties remain. So the verdict is still out. But here's what's certain. Whatever explains cosmic acceleration, whether it's vacuum energy, quintessence, or modified gravity, it reshapes our understanding of nothingness. Because nothing in physics no longer means absence. It means potential, it means structure, it means weight. Let me say that again. Nothing has weight. Not because it's heavy, but because energy and mass are equivalent. Not because it's full, but because emptiness at the quantum level is unstable. Not because we've measured it on a scale, but because we see its effect in the fatting light of ancient supernovae, in the whisper of entangled fields, in the silent expansion of the night sky. And now, as you drift deeper into rest, let this settle. The vacuum is not a void. It is the ground state of the universe, the canvas, the medium, the stage, and the actor. It gives particles mass. It pushes galaxies apart. It hums with transient life, virtual particles dancing in and out of existence, too brief to see, too real to ignore. You are floating in it right now. Your thoughts, your breath, the slow rhythm of your heart, all unfolding within this energetic stillness. And if in a dream you find yourself in an endless white space, featureless, silent, calm, remember, even there the fields are vibrating. Even there the energy is non-zero. Even there space has weight. Not enough to hold you down, but enough to shape the cosmos. So rest now. Let the quantum fluctuations ripple through your awareness. Let the 0-point energy resonate in your stillness. You are not separate from the vacuum. You are a localized excitation, a coherent pattern in the same fields that fill the void. And in that unity there is peace. Because the universe, even in its emptiest moments, is never truly empty. It is waiting. It is humming. It is gently holding you. Good night. May your rest be deep, your thoughts quiet, and your dreams gently shaped by the same quantum fields that hum through the cosmos, steady, silent, and full of potential. Sleep well.